Camera-based heart rate estimation has been widely explored as a non-contact modality to improve human lives. For example, in telemedicine, while a person is Skyping with a doctor, the doctor can then easily have access to the vital signs like the heart rate and the heart rate variability extracted from the face video. In cars, heart rate extracted remotely can be used to continuously monitor the health or the engagement of the driver, and this might help in reducing the chances of accidents. Camera-based heart rate estimation can also be used for neonatal monitoring, where any contact-based modalities might increase the chances of infection. A camera pixel can capture the periodic blood volume changes arising from heartbeat. The modulated pixel intensity from the face then gives us important clinical metrics like the heart rate. However, the signal is very weak and is often drowned in noise. Further, facial movements of the person introduce large distortions in the recorded pixel intensity fluctuation. And these distortions make it challenging to obtain a reliable estimate for the heart rate. In this video, where the person is moving, the light intensity at any point on the face changes with the head rotation movement. The recorded pixel intensity then consists of a small pulsatile heart rate signal called the PPG signal, along with a very large signal which arises from the movement of the person. Ideally, the spectrogram of this clean PPG signal indicates a strong dominant signal at the heart rate frequency. However, the spectrogram of the recorded pixel intensity is severely distorted due to the presence of motion artifacts. Often, the frequency of the movements overlaps with the heart rate frequency, and therefore reliable estimate of the heart rate becomes very challenging to obtain. So given a face video of a person with movements, the main goal is to extract a very high quality PPG signal and finally have an accurate estimate of the heart rate. The first step towards handling motion is by using a face tracker. Given a video of the human face, a face tracker detects the landmark points like the eyes and nose and tracks them across all the frames. Next, within the detected face, the color intensity change is tracked at each pixel. So if we plot one single pixel from the face region, we'll mostly have three signals corresponding to the red, green, and blue color channel of the camera. Now, generally, even if the face tracker is perfect, there will still be motion distortions in the signal. And one of the earliest attempts to extract the PPG signal was to use a blind source separation technique like ICA or PCA that decomposes these three color intensity signals into three uncorrelated signals. And one of these signals would be the PPG signal that we are mainly interested in. But all the existing prior work tries to filter the distortions by some kind of implicit motion cancellation. In our approach, we explicitly model and generate motion signals using inverse rendering. Our key approach is to use a light reflection model to relate facial movements to the motion artifacts in the measured PPG signal. We then use these generated signals from the rendered video in a motion cancellation step to filter the distorted pixel intensities, thereby resulting in a very clean signal and an accurate estimate of the heart rate. Next, we will discuss the signal model that we use to generate the motion artifacts from the input video. Under the assumption that the human face is a Lambertian surface and a distant lighting condition, the light intensity from the skin surface is given by a following model where R is any point on the face. The surface normal at the point is given by the unit vector N, and the light direction is given by the unit vector L. The light intensity is directly proportional to the dot product between the surface normal direction and the light direction. And this part is called the shading. The shading term is then scaled with the skin albedo or skin color and the light strength I0. The skin color is dependent on the melanin content of the skin and also the pulsatile PPG signal caused by the blood volume changes, which is the main signal that we want to recover. Here, E denotes the strength of the PPG signal and is very weak compared to the average skin color. Now, whenever there are facial movements, the location and the orientation of the facial point changes with time. And hence, the temporal changes in the shading part is responsible for distorting the measured pixel intensity at the camera. Now, to recover this PPG signal in presence of distortions, our goal is to first eliminate the shading part and thereby generate the motion signal. Now, we will then use this motion signals to filter out the pixel intensities. So first, to estimate the motion signal, we need to access both the facial geometry as well as the lighting. So first, we estimate this facial geometry. To do that, we use a 3D morphable models for face fitting, which outputs the approximate 3D facial geometry for each frame in the video. First, the face is detected and tracked for each frame, and then a fitting process generates a dense triangular mesh on the face. The 3D location of these small triangles is then used to estimate the surface normal at each centroid of the triangle. We also compute an average of pixel intensities inside each triangle locally. So for each small triangle on the face, we have surface normal estimates which look like this at each frame, and also the average pixel intensities in red, green, and blue channels. Next, we need to estimate the effective lighting direction from the given video. Here, we consider only a single light direction, but even if multiple point sources are present in the scene, all the sources can be modeled as one single effective point source under the assumption of a Lambert surface. Also, if a PPG signal is weak, we can ignore the contribution of PPG signal and write the following expression. So here, I contains the pixel intensities from all the regions on the face. K is the total number of triangles or point on the face, and T is the time duration considered to estimate the lighting. Now, the time duration should be ideally greater than the periodicity of the PPG signal. The N, which is the estimated surface normal direction for all the point on the face, is also of this dimension K times T cross 3. So in this expression, both the surface normal and the pixel intensity measurements are known, and the effective light source direction L and the average skin color C need to be estimated. Using this expression, the matrix L times C is obtained by solving a least square problem in an overdetermined system. Further, this matrix is a low-rank matrix in a simple lighting environment. Hence, we compute the singular value decomposition on the estimated matrix L times C transpose to separate the light source direction and the average skin colors C. So once we estimate these two parameters, we generate the motion signal M in each facial point by inverse rendering. Here, M contains the generated motion signals. In essence, these are the signals that capture only the distortions in the camera pixel intensities and is devoid of any PPG signal. So here we show examples of the recorded pixel intensities versus the generated motion signal for two different type of motions. Here, the signals are obtained from a point on the left cheek of the person. Note how the intensity varies due to changes in the surface orientation, which is accurately captured by the rendered video. The pixel intensity has the motion distortions and the PPG signal of interest. On the other hand, the rendered face only contains the motion distortions. Here, the head rotation movement has a periodic fluctuation, which depend on the speed of the rotation. And in case of a talking scenario, the intensity fluctuations are smaller than the head rotation, but has faster fluctuations. Overall, we observe a very good agreement in the generated motion signals and the intensity fluctuations. Next, we use the pixel intensity along with the generated motion signals to extract a clean PPG signal using a filtering process. In this work, we adopt a bidirectional long short-term memory network as the filtering technique. The pixel intensities and the reference motion signals are used as input to a 3-layer bi-LSTM network with 30 hidden units. For training the network, we use datasets with videos of human subject performing facial movements. The contact-based pulse oximeter waveforms in the dataset serve as ground truth levels. We then train this architecture with Adam Optimizer, which optimizes the mean square error loss between the predicted PPG signal and the target ground truth waveform. The heart rate is then estimated using the predicted signal from the network. To quantify the improvement in performance, we evaluate the signal quality in terms of signal to noise ratio SNR and the root mean square error in the estimated heart rate. In both type of movements, the talking and the head rotation, we observe an average of over 2.5 dB improvement in the signal quality over the second best prior method. We also observe an improvement in the root mean square error of the estimated heart rate using our proposed approach. In all the cases, therefore, our proposed method achieves no greater than 3 beats per error, 3 beats per minute error in the estimated heart rate, and therefore this can prove to be useful in many clinical settings.